Welcome back to my course Aspects of Biochemical Engineering. In the last couple of lectures, I tried to discuss the immobilized enzyme system, because initially I told that what we mean by immobilized enzyme, and I told that immobilized enzyme is nothing but confined or fixation of the cell on the solid matrix, and then I try to discuss what is the advantage of using this immobilized enzyme system. Then I also try to tell you that what are the different immobilization techniques we have, and what is the methodology on the basis of that you can select the immobilization technique. And one thing I highlighted that all immobilization technique is not suitable for all enzymes, because whenever we select any kind of immobilization technique, we shall have to first select the criteria. Because whether we are looking for easy preparation or we are looking for strong bonding between the solid matrix and the enzymes, and all this criteria is very important. And during this lecture, we emphasize on couple of things. One is the characteristics of the solid matrix, and that plays very important role. And we also discuss about the porous and non-porous solid matrix, how it affects in the immobilized enzyme system. Now, today we already discussed the kinetics of enzymatic reaction, and in this kinetics of enzymatic reaction, we assume the enzymes they freely interact with the substrate. So, we consider that as a homogeneous system. Whenever we consider that immobilized system, I told you previously that usually the enzymes are fixed on a solid matrix. Now, solid matrix is insoluble in water. So, and your substrate is actually present in the soluble form. So, as soon as even your enzymes is soluble, when you fix on the solid matrix, the things will be insoluble. And so, there is a presence of two different phases, one is solid and the liquid. So, this is an example of the heterogeneous reaction system. Now, in case of heterogeneous system, that what we have your bulk, you have the substrate. The substrate has to diffuse from the bulk to the surface of the solid matrix, and where the enzymes are located, and let the reaction take place. And after the reaction is over, that whatever product formation is there, that product will diffuse from the surface to the bulk, and then and only then we will get the product. So, this kinetics that we are going to discuss, that how this heterogeneous system kinetics can be used for explaining the immobilized whole cell system. The first that let us discuss about that immobilized. What do you mean by immobilized enzyme system? Normally include, as I told you, the insoluble immobilized enzyme and soluble products and substrate and products. So, what I told that suppose this is a solid matrix and this is insoluble, and here the enzymes are, this is the enzyme. So, when it fixes on the solid matrix, so this will be insoluble. Now, when you pass your substrate like this here, and this substrate is soluble, and this substrate when comes here, and this has to diffuse on the surface of the solid matrix, then and only then it will interact with the enzyme and product will form. As soon as product is formed, product has to diffuse out to the bulk. So, that diffusion one of the important aspects of the heterogeneous system, and that is why we have written that mass transfer resistance plays very important role in case of heterogeneous reaction kinetics. Now, mass transfer resistance may be introduced by the immobilized system, which is absent in the free enzyme solution. Now, when you have, suppose this is the reactor, in this reactor when you have this enzyme and substrate. So, when they are soluble, they can freely interact with each other, there is no diffusion problem. But as soon as this is insoluble, then substrate has to diffuse from the soluble, that from the liquid to the surface of the solid matrix, and then only the reaction, as I mentioned before. Okay. The mass transfer resistance occur due to large particle size of the immobilized enzyme and due to inclusion of the enzymes in the polymetric polymetric matrix. So, you know that that mass transfer limitation, I can tell little bit in details. Suppose this is the pore of the solid matrix, inside the enzymes are there. So, naturally when substrate is there, here substrate has to diffuse inside this, and then and only then it can interact with the enzyme, and when product form, product has to diffuse out from the surface of the solid matrix to the bulk. This is we call bulk. Now, transportation of substrate in immobilized system, how the transportation take place. Now, you look at this, you see that the transfer from the bulk liquid to the relatively unmixed liquid layer surrounding the immobilized enzyme system. So, this is I can explain on the basis of this. You see that here this is the substrate, am I right? This is the substrate, and this is be diffused. This is the solid surface, and across the solid surface there is a fine layer, and this we consider as the unmixed layer. You know that. So, that is exactly what we have written here, that transfer of the bulk liquid to a relatively unmixed layer, liquid layer surrounding the immobilized enzyme, and diffusion through the relatively unmixed layer, then diffuse take place, and diffusion from the surface of the particle to the active sites of the enzyme, which is inner support material. Now you can understand. Here let us assume that this is the enzyme we have inside that. This is the enzyme. So, substrate is diffused, this is the unmixed layer, then diffused into the surface, then it goes inside the solid matrix. This is the inner. So, 1 and 2 steps are the external mass transfer resistance, and third step is the intra-particular mass transfer resistance. So, this is the SB is the bulk substrate concentration, and this is the catalytic surface. When it goes the surface, this is SS. If you consider this is SS, SS means the substrate concentration at the bulk of the solid matrix. So, you know that this is the gradient that we have. This is concentration, most of the cases usually less as compared to, all cases is less as compared to this bulk substrate concentration. And what is the gradient here? SB minus SS or S that we have here. In this we have considered the substrate concentration at the bulk as S. Now, question comes how you can calculate the external mass transfer resistance. Now, here I want to point out that suppose this is a solid matrix and enzymes are immobilized on here. So, when you have this is the bulk substrate concentration. So, it is at the surface, it like this, the external surface, this is called external surface, and when the enzymes are inside this solid matrix, we call it internal surface. So, or you know that suppose it is inside the pore, then it is inside the internal surface. So, if the enzyme is immobilized on the surface of the insoluble particle, the path is only composed of first and second step, what you call external mass transfer resistance. So, as for example, if we consider the nylon solid matrix and with surface is we have little pore inside. So, in that case that the enzymes will remain at the surface of the solid matrix. Now, in that case, how you can express the mass transfer? Mass transfer can be expressed as Ns equal to Ks into A Sb minus S. Now, I told you that here this is the enzyme and here S is the substrate concentration. In the bulk we have substrate concentration Sb. So, what is the dragging force we have? Sb minus S. This is the concentration gradient and this is the mass transfer coefficient. This is Ks is the mass transfer coefficient, A is the interfacial area, the how much area this mass transfer take place. So, we have what we have written here, Sb and S are the substrate concentration in the bulk of the solution at the immobilized enzyme surface respectively, and Ks is the mass transfer coefficient, unit is the length per unit time, and S is the surface area of the immobilized system per unit volume. Per unit volume means this if A is the surface area and volume is B, that is the per unit volume. That is A is like this. Now, that that very interesting thing is that if you look at the reaction, because here the reaction how it is taking place. Suppose this is the enzyme and this is the substrate, that is the diffusion, and this the S is the substrate concentration. So, what will be the velocity of reaction? Because the velocity of reaction will be V equal to V max S Ks plus S. Km plus S, am I right? Not Ks, Km plus S. This is the what exactly we have written. This is the velocity of reaction. Now, this is the mass transfer, am I right? Now, under steady state condition, now what do you mean by steady state condition? Steady state condition means rate of substrate diffuse from the bulk to the surface and rate of reaction. If the rate of reaction and rate of diffusion they are same, then and only then substrate concentration in the surface of the enzyme, surface of the solid matrix will be constant. Now, if suppose rate of diffusion is more, substrate diffusion is more than rate of reaction, then what will happen? The substrate concentration on the surface of the solid matrix will increase. Now, if rate of substrate diffusion is less as compared to rate of reaction, then what will happen? More substrate will be consumed. The substrate concentration at the surface of the solid matrix that keep on decreasing with the time. So, steady state condition will be what? When rate of mass transfer equal to rate of reaction. And how we can write? This is how what we can write, Ks into A Sb minus S equal to V max S Km plus S. This is how we can write. Now, this shows the relationship between substrate concentration in the bulk of the solution and the surface of the immobilized enzyme. So, this we can visualize from that. Now, this equation, if you look at the previous equation that we have, what we have? This is we have the case what we have? We have Ks into A, what we Sb minus S equal to V max S Km by S. Am I right? So, now the interesting thing is that suppose Ks A and Sb you can take common, then this will be what? S by Sb. Am I right? Now, here if you divide this with Sb, then what we can write? V max S by Sb by Km by Sb plus S by Sb. Can I write like this? Now, if we assume x s equal to S by Sb, then I can write what I can write? This is equal to this equal, and we can assume that NAD, what NDA? NDA is the Damm-Kohler number. What is the Damm-Kohler number? Damm-Kohler number you can see this is what? V max. Am I right? And this is what? KSA into Sb. Now, what is V max? V max is the maximum. So, what is the V max? So, I was talking about the NDA. Am I right? What is the NDA? Is the V max into Ks A into Sb. this is Vmax. What is Vmax? Vmax is the maximum velocity of reaction. Velocity of reaction. Am I right? Now, what is this? Well, what is the rate of mass transfer? Mass transfer equal to the Ks A, rate of mass transfer Sb minus S. And when it will be maximum? When this will be equal to 0. So, this is the what we can do, this is the maximum mass transfer rate. Am I right? So, Damkohler number is nothing but ratio between the maximum velocity of reaction and maximum mass transfer rate. That is how we can define this. So, this is exactly, if we put all this value, we will come across this equation. We will come across this equation, that 1 minus xs NDA equal to k xs 1 plus k xs. Now, k is equal to Sb by Km, Sb by Km, that we can easily find it out. Now, from this equation, what we can conclude? This equation, that what we can conclude? Conclusion is that if NDA is greater than 1, then the mass transfer rate is much higher than the reaction. So, the overall reaction is controlling by the enzymatic reaction. Let me tell you what is the NDA. I told you. What is the NDA? I told you NDA equal to what? Vmax by Ks into A into Sb. That means the maximum velocity of reaction by maximum rate of mass transfer. Now, if Ks is less than 1, that means what? That this should be very high, rate of mass transfer will be very high. So, you are the substrate is going at the higher rate than as compared to the rate of reaction. Then what will happen? The mass transfer is much greater than the reaction, and the overall reaction will controlled by the enzymatic reaction. So, the velocity of reaction, what is the limiting factor here? The limiting factor is the enzymatic reaction, because your rate of mass transfer is more. So, then if you want to improve upon the rate of reaction, then what will we shall have to increase the velocity of reaction, and which is nothing but Vmax Sb Km plus Sb. Now, what is the next case? Next case, what is that? Is NDA is greater than 1. Then velocity of reaction is more as compared to the mass transfer. So, in that case, the velocity of reaction, that is not an important factor, that limiting factor. Limiting factor is the mass transfer. What is the mass transfer? Mass transfer is equal to the Ks As into Sb. That is the maximum mass transfer. So, this is the first order with respect to bulk substrate concentration. This we can write this expression like this. Then there is another important term that is associated with the immobilized enzyme system or heterogeneous reaction kinetics, that is you have effectiveness factor. What is the effectiveness factor? Effectiveness factor is the actual reaction rate, the rate if not showed by the mass transfer. What does it mean? It means that suppose this is a solid matrix and your enzymes are immobilized on here. So, here the substrate concentration is S and bulk is the substrate concentration Sb. Now, what is the actual rate of reaction depends on this substrate concentration. Now, when rate divided by rate if not slow by mass transfer, that means if the all substrate is available at the surface, then that is if this is not slow by mass transfer, that means here S will be equal to Sb and this will be As. So, what is the effectiveness factor? Effectiveness factor is the actual rate of reaction divided rate of reaction when there is no mass transfer limitation, because all substrate are available for the reaction. So, this is how we can write. This is when S is the surface that the concentration S, we can write this equation. When in the bulk you have all substrate available for the reaction is this, and if you write in this form, the final equation we will get in this form, because I have already prepared this to explain what is K and Xs, all this thing I explained. If you solve it, we can find this equation. Now, here I want to point out one thing. Now, if eta cannot be more than 1, am I right? The maximum rate of reaction will be what? That when all bulk substrate concentration available for the reaction. Now, so eta value will be maximum, it will be 1. Now, if it is 1, I can assume that there is no mass transfer limitation problem. So, your heterogeneous reaction system will tends to the homogeneous system. Now, when the eta value is less than 1, if it is less than 1, then what is happening? That means your mass transfer diffusion problem is there. That means the actual rate of reaction will be less as compared to that of when all substrate available for the reaction. So, the eta value when it is less than 1, then we have mass transfer problem. So, here there is no mass transfer problem. I hope you understand that. Now, how you explain that? That that if you look at Xs, what is Xs? Again, let me write it. Xs is equal to what I told S by Sb. What is L? S is the substrate concentration at the surface of the solid matrix. Sp is the bulk substrate concentration. Now, if you say X equal to 1, then what will happen? That concentration at the surface is equal to the bulk substrate concentration. Then eta value will be 1, which indicate there is no mass transfer limitation, what exactly I point out before. But when Xs is tends to 0, that means that that this is very high as compared to this S, Sb is very high as compared to S, then the mass transfer is very slow as compared to the reaction rate. I hope you understand that. Now, this is about the external mass transfer. Now, let me switch over to the internal mass transfer, when the particles, that enzyme present inside the porous solid matrix. Now, let us consider the case of enzyme immobilized system is spherical particle, porous biocatalyst. Now, assumption is that the particle is isothermal. Isothermal means you control the temperature is constant, and mass transfer occurred by diffusion only, and diffusion rate can be expressed by using the Fick's law with constant effective diffusivity, and then the particle is homogeneous. It is homogeneously distributed in the solution, and particle is at a steady state, and substrate concentration varies with the single spatial variable. So, if we assume all these things, then we can write this. Here we can see that this is the core of the solid matrix, and here the substrate is diffusing it, how it diffuses to the, and let us assume this is the fraction that which is we consider a del r. This is the fraction. Then we can integrate from 0 to r, that we can integrate there. Imagine a thin spherical cell thickness of del r located at the radius r from the center. Okay, let us assume that. Now, here we can see that in the rate of input will be what? It will be equal to dEs. dS is the diffusivity, and ds by dr into pi r 4 pi r square, because since we are considering the spherical spherical particle, the surface area of the sphere is about 4 pi r square. So, this is r plus del r, and what is the output that we have? This is r, that this is r, we get ds equal to r, that is. the rate of generation is equal to 0, because this, since substrate is diffusion take place. Rate of consumption I can assume minus R is equal to this. This is the R is into volume, and this is 4 pi R square into del R is the nothing but volume. And rate of accumulation at the steady state condition is 0, and DES is the effective diffusivity of the substrate S. Substrate is the concentration of S in the particle, and R is the distance. Then what is our equation that we have, that during the reactor analysis we use that equation for material balance equal to rate of input equal to plus generation equals the output plus consumption plus accumulation. Now here, what is the rate of input? This is DES into ds by R in 4 pi R squared. What is R plus del R? And what is the output? That generations, no substrate generation take place, that is equal to 0. And what is the output? This is the output as R. And then this is the rate of reaction, R minus R squared into 4 pi R square into del R, and a rate of accumulation that should be equal to 0. Then we will finally reach this equation. And now if you divide this 4 pi del R, give this equation. So we will come across this equation, and then from this we can find out this equation. When del R tends to 0, then we can put a limit, then we can find this equation there. Now finally we come across this steady state, that cell mass balance is like this. Under steady state condition, this d del this value, this will be equal to minus R square, and this if we now we can differentiate this, then we will get this kind of equation, and finally we come across this equation. A differential equation representing the diffusion reaction of the spherical catalyst here. Now finally we come across this equation of the steady state, this DES d2 S by dr2 plus 2 by R ds by dr equal to minus R, and this equation I can write in this form. And then we can put the boundary condition as the R equal to small r when equal to bigger, S will be equal to SB. That we have seen that thing, that this here is the SP and here is the S. So when this R equal to R, then S will be equal to RC. When R equal to 0, this rate of mass transfer will be equal to 0. Now if we assume non-dimensional parameters, if we assume like this, now previously this we assume at the XS, but in this case we assume this as the S bar to understand differently, that S equal to for internal diffusion, this is S by SB, the same thing, only we use the terminology, or R bar equal to a small r by capital R, then this equation, the previous equation, can be rewritten in this form. So finally we come across this equation. This is the equation that we have, and again if we put the boundary condition, this R bar equal to 0, then d S bar by d R bar equal to 0, R bar equal to 1, S bar equal to 1, then this equation will come across, this particular equation. Now finally the right hand side, if you look at the right hand side, this is this one. I can write this equation in this form, and this is equal to R square V, and d km you can take it out. This I can write S by SB 1 plus that just we divide by SB, we can get this equation, that we can write this equation like this. Then the right hand side again we can write in this form, And what is this form? This is, if you look at, this is constant, what we have written before. Now this is equal to S bar. S by I told you S bar equal to what? S by SB. Am I right? So we can, this is equal, and beta equal to what? Km by SB. So we can write in this form, and finally we come across this equation is the 9 phi square, then S bar by this. What is phi? This is called phi modulus. This is phi square equal to this, and this is equal to mass maximum reaction rate and divided by maximum mass transfer rate in case of intraparticulate matters. Then this is, then phi square equal to, this is, we can write in this form. This is the final equation I can write. So now we go back to the effectiveness coefficient we have explained before. That is what is the effectiveness factor? That observed reaction rate divided by rate if not slowed by the mass transfer. So this can be explained like this: when there is no mass transfer limitation. The part of that means that this is actually the ratio of the performance of heterogeneous system divided by performance of the homogeneous system. As I told you that when eta equal to 1, that means your heterogeneous system is equal to homogeneous system. Now when it is less than 1, that means your how, then we have the mass transfer limitation problem in this. This is how the eta can be explained. Now this is we can write that in case of zero order reaction, that beta tends to 0, then eta equal to 1, that I shall explain you, and eta can be correlated with phi modulus in this particular equation. Now this equation, this graph tells us the correlation between eta and phi value. This is phi modulus and this is effectiveness factor. Now if you find out, if you 0.3, that is that it is the rate of your eta is equal to 0, and but if it is more than 0.3, then your eta value is less than 1, that is your mass transfer problem is more. Now here, if beta is equal to 0, it considered as 0 order, and when beta is tends to infinity, it is considered as a first order reaction. Now finally we come across that in many practical cases that it is difficult to evaluate the kinetic parameters Km and Vmax, which is Michaelis Menten constant and maximum velocity of reaction. So a way of circumvent that problem is to apply the observable Thiele modulus, sometimes called the Weiss modulus. This is equal to phi equal to Vp by Ap. What is Vp? Volume of the particle. Ap is the area of the particle. This is Rs is the observed rate of reaction, and DES is the diffusivity, Sb is the bulk surface concentration, and this is called intrinsic kinetic parameters. Now this is the final thing that we have. If phi value is less than, from the figure we have seen that if the less than 0.3, then eta is close to 1, then the limiting region is the reaction and mass transfer resistance is negligible. Now when eta value is greater than 3, then this eta is inversely proportional to phi value, then it will be diffusion resistance. The mass transfer resistance will play the very important role. So in conclusion, in this lecture what we try to learn that how the heterogeneous reaction kinetics can be explained. Now heterogeneous reaction kinetics, the substrate has to diffuse from the bulk to the surface of the solid matrix, then only then reaction takes place. Two type of diffusion phenomena that works. One is the external mass transfer and the internal mass transfer. Now how this the two parameters we have come across, one is damp polar number and that is the effectiveness factor. What is damp polar number? Damp polar number is the maximum velocity of reaction divided by the maximum mass transfer. What is effectiveness factor? Rate of reaction, actual rate of reaction divided by rate of reaction when there is no mass transfer limitation. So, when eta value is 1, your heterogeneous system tends to homogeneous system. When eta value is less than 1, that means there is a mass transfer problem. How it is related with high modulus, that we try to explain in this particular lecture. Thank you very much.